Hi, welcome to chapter 19, aldehydes and ketones and the nucleophilic addition reactions. Okay, my name is Ramon Rios, I am professor of organic chemistry, and this is a recorded lecture in order to help your study. This is not in any case a substitution of the attendance to the lectures. Remember that the attendance to the lectures is mandatory in Khalifa University. Okay, then what we will do in this chapter? Basically, in this chapter, what we will do is we will name aldehydes and ketones, we will talk about the nucleophilic addition reaction of aldehydes and ketones, and finally we will check the nucleophilic addition of hydrogen cyanide or cyanide to form the cyanohydrin. Okay? Well, the first thing is that if we check, aldehydes and ketones are present in a lot of natural products and pharmaceuticals. Here you have an example of a natural product, pyridoxal, that contains an aldehyde here. Okay, here. And we have a hydrocortisone that has two ketones in these two positions. Okay, we will start naming the aldehydes. How we can name the aldehyde? Okay, the thing is very similar to what we did before. Is we have to find the main chain with the major number of carbons that contains the major number of aldehydes. Okay, again, if we have a compound like this, the main chain will be this, that contains the two aldehydes and not this one that, despite contains more carbons, doesn't contain the major number of aldehydes. Okay? Then when we know this, when we find the major chain, what we need to do is to name the major chain. For example, methane, propane, ethane, octane, etc. And we change the E at the end for al. This is how we know that we have an aldehyde. The aldehyde, the name finished by al. Okay, if we compare the aldehyde with all the other functional groups that we studied this year, this is the one that have major priority. Okay, that means if we have a hydroxyl group, for example, the aldehyde will be the major group, the main functional group. Okay, for example, here we have some compounds. This is a 2-carbon major chain. That means will be ethane, and then we put al, ethane, al. Here we have a 3 carbons, will be propan, al. Here we have a 5-member carbons, okay, and we apply exactly the same rules that we applied before. We start numbering for the lowest numeration of the aldehyde, that means position 1, and this will be, if it's 5 carbon, will be pentanal, and then we add the substituents, that means will be 2-ethyl, 4-methyl pentanal. Remember that the ethyl and methyl are in order alphabetical. Okay? One difference is that when we have a directly attached aldehyde to a ring, then the naming is we name the ring and then we put carbaldehyde at the end. Okay? And this ring, the position 1 will be always the position of the aldehyde. That means here this will be a cyclohexane, and then we add carbaldehyde. Here will be a naphthalene carbaldehyde. Okay? As usual, a lot of aldehydes has a common names. The 1-carbon aldehyde is called, instead of methanal, normally is called formaldehyde. The 2 instead of ethanal is called acetaldehyde. With a double bond is called acrolein instead of propanal. If we have this compound with a double bond in the middle of a butanal, instead of 2-butanal is called crotonaldehyde. And for example, when we have a benzene attached directly to a aldehyde, instead of benzene carbaldehyde, the name is benzaldehyde. Okay? How we name a ketone? Okay, we name a ketone. Basically, the only difference with the aldehydes is that ketones can be in the first or in any position of the carbon chain. Aldehydes, because of his structure, can only be in the first or the last position of the carbon chain. Okay, here the ketone can be in any position. That means we have to cite the number of the position where is the ketone. And then ketones, we name the major chain. We have to find the major chain, the major number of carbons that contains the major number of ketones, exactly the same that with aldehydes. Okay? When we have this, we name the chain. For example, here we have a 6-member chain. Okay, that means will be hexane. Then the ketone is in position 3. We start numbering from here. Why? Because the numeration of the ketone is lower from this side. That means will be a 3 hexane, and then we put the suffix that indicates that we have a ketone. And the suffix for a ketone is on. We remove the E and we put on. That means that this will be 3 hexanon. Here, for example, we have 1, 2, 3, 4, 5. This will be a pent, the position, no, 6 again, sorry, 2, 3, 4, 5, 6. This will be a hexane on. Where is the ketone? In position number 2, that means hexane to on, or 2 hexane on. But now we have a double bond here. The double bond is in position number 4. Remember that we start numbering from here because the ketone has to have the lower numeration. That means that we will have a 4 hexane 3 on, or X 4N 2 on. And finally, we can have this compound, okay? And this is again 6 carbons, the main chain, and this will be, we check the number of ketones. We start counting here in order to give the lower number possible. This will be a 2,4 ketone. That means the name will be 2,4 hexane dione. Why the D? Because we have 2 ketones, or hexane 2,4 dione. Up to you. Okay? Again, there are some ketones that has a common name that is not the UPAC name. For example, the free carbons ketone is called acetone. It's the liquid that you use for the nails to remove the pain of the nails. When we have a phenyl and a methyl in each side of the ketone of the carbon double bond oxygen, it's called acetophenone. And if we have 2 phenyls, it's called benzophenone. Okay, if we have a functional group that has a higher priority than ketone, for example an aldehyde, then the ketone is a substituent, and then is called with the position where is the ketone, and instead of on we have to put oxo. For example, here we have an aldehyde that is high priority. That means that this will be 1, 2, 3, 4, 5, 6. Will be hexanal because it's an aldehyde, and then we put the number of the ketone with the termination oxo. This will be a free oxo hexanal. Okay? Good. What we can do is problem 19.1 now. Here we have a ketone. The main chain will be this. 1, 2, 3, 4, 5. That means there will be a pentanon, and the oxygen is in position 3, whatever side we choose. That means this is a grow. We go to the next substituent. Then we have to put the substituents in the lower numeration. That means that we have to start from here. This will be a 2-methyl pentan 3 on, or 2-methyl 3 pentanon. Okay? Here, this is the main chain, will be a propanal, and will be free phenyl propanal, because we start counting here to put the aldehyde with the lower numeration. Here we have a diketone, and it's a 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons. Okay, and the ketones are in position 2 or 6, because if we starting from this side, because if we start from the other side, the numeration will be higher. This will be a octanon, that means octa 2,6-dione or 2,6-octadione. Okay, remember that we have to put the D because we have two ketones. This one is an aldehyde directly attached to a cyclohexane. That means that the name will be cyclohexane carbaldehyde, and then we have to check the substituents. Always, this will be the position 1 of the cycle. That means that the methyl is in position 2, will be a 2-methyl cyclohexane carbaldehyde. And now we add the stereochemical information. If we check, the CHO is going down and the methyl is going up. That means that this will be a trans 2-methyl cyclohexane carbaldehyde. Okay, here we have another aldehyde, and this is 1, 2, 3, 4, 5, 6. 6, this will be a hexanal, but we have a double bond. That means that will be 4, because we start counting here, 4 hexane null. Okay, and finally, compound F, the main chain will be the cyclohexane, and this will be a cyclohexanone, and then we put the substituent. The ketone will be always the 1, this will be 2, this will be 3, 4, 5. 2,5-dimethyl cyclohexanone. Okay? Good, then for home, please do problem 19.2. That is very easy. If you have any question, please send me an email and I will try to answer all your questions. What about reactivity of aldehydes and ketones? Well, the reactivity of aldehydes and ketones basically is due for the properties of the carbonyl group. This is the carbonyl group, a carbon bonded by a double bond with an oxygen. That means that the oxygen is more electronegative than not the carbon. This will be a density negative charge, and the carbon will have a density positive charge. Okay, because the carbon is a density positive charge, a nucleophile that is a friend of positive charge, will attack this position. The attack will take place following this approach, okay, that is around 104 degrees of the carbonyl group. That means it's called a Burgit-Zinitz trajectory. Okay, that means the nucleophile attacks the carbon, and in order to don't break the octet, to don't expand the octet, the pair of electrons that are forming the carbon double bond oxygen are going to the oxygen, forming this intermediate. And then the next step is we protonate the oxygen negative, we add a proton, we add acid or samsic acid, and we generate the final alcohol. Okay? Normally, the addition of a nucleophile to a ketone or an aldehyde, what will give us is an alcohol. Here you can see a list of different nucleophiles. Anionic, that means that are anions or that are neutral nucleophiles. Okay? Basically, in order to be a nucleophile, the only that you need is a pair of electrons. Remember that always charged anions that are nucleophiles will be more reactive than not the neutral. Okay, here you have two examples of how it's working. The nucleophile attacks the carbonyl. We form this intermediate. Remember, the nucleophile forms a carbon, form a bond with the carbon, and then the double bond between the carbon and the oxygen are going to the oxygen in order to avoid expand the octet. Then we protonate and we generate the alcohol. Okay, then which is more reactive, an aldehyde or a ketone? Well, basically always will be more reactive an aldehyde. Why? There are two reasons. One reason is because, for example, if we have an aldehyde or a ketone, the reactivity is coming because this carbon has a density positive charge. That means how we stabilize positive charge. We can stabilize positive charge with carbon groups around. That means, for example, remember when it's more stable a carbocation, when more substituted is the carbocation. Why? By hyperconjugation. Remember that they are overlapping between the pz orbital and the sp free orbital of the carbon that is one carbon away of the carbocation. Then, of course, if we have a primary carbocation, that will be the example of an aldehyde. Okay, we only have one substituent. What is happening is that, what is happening is that we only have one stabilization, while in the ketone, we always have two stabilizations. That means ketones, the positive charge will be more stabilized than not in the aldehydes. If the positive charge is more stabilized, that will be very less reactive. Okay? Yeah. That means aldehyde will always be more reactive than not ketones. And what happens if we have an aromatic? Well, for example, an aromatic aldehyde, but this is exactly working the same in the case of aromatic ketones. Okay, in the case of aromatic aldehydes, we have an extra way to stabilize the carbocation here. Okay, here you have the carbocation. Okay, we put these 2 electrons on the oxygen, and we can stabilize this carbocation in this carbon by resonance form with the aromatic ring. When more resonance forms, more stable will be. That means if we compare an aromatic with an unaromatic, with an aliphatic here, aliphatic has only one resonance form, while the aromatic has 4 resonance forms. That means it's more stable, that means will be less reactive. The same for ketones. If we have a aromatic ketone, for exactly the same reason, for stabilization of the positive charge by resonance, will be less reactive. Okay, here you have an example of reactivity. Check that when we are doing exactly the same reaction, addition of water to an aldehyde or to a ketone, with the aldehyde we have a 99% conversion, that means all the reaction is done, while with the ketone only 1% is done, because it's by far less reactive than not the aldehyde. Okay, finally we will talk about the cyanide addition to the aldehydes and ketones, and basically it's exactly the same. We have the cyanide, that the cyanide is this compound that has a negative charge on the carbon. This pair of electrons of the carbon attacks the carbonyl. Again, when we form this carbon-carbon bond in this case, the double bond between the carbon and the oxygen is going to the oxygen to forming this intermediate. Then we protonate and we get this compound, that this is a cyanohydrine. Okay, and these compounds are very important intermediates in organic synthesis. Right? Another typical reaction that we can do is the reduction. In order to reduce, we use our old friend, sodium borohydride, that is the same, exactly the same, than a hydride negative. Okay? That means this hydride negative attacks the carbonyl group, exactly the same than before. The pair of electrons, when we are forming the hydrogen-carbon bond, the pair of electrons that are forming the carbon-oxygen bond are going to the oxygen in order to avoid to break the octet, and then we protonate to generate the final alcohol. Okay? It's easy, it's working with ketones and with aldehydes. Normally aldehydes are by far more reactive than not ketones. And that's all for this chapter. Please study the questions of the book 1, 2, 5, 6, 7, and 31, and read the textbook chapter 19, points 1, 4, and 6. And thank you very much for your attention. See you in the next lecture.